are we going to play or not?
I'm sorry, I just can't get into it.
That was pitiful if you can't hit those kind. Okay, one more time. Okay, Todd, let's take a break, all right?
Yeah, all right.
Oh, me. It is hot out here.
Yeah, it is. You know, you're going to think this is dumb. But ever since Frank gave us those study packets, I see geometry everywhere.
Yeah, Todd, you're right. I do think that is dumb. Man, he just messed up our whole game.
Well, I know, but have you really ever thought about how much geometry is on a tennis court?
No, I never have, and if I did, I try not to think about it.
No, I'm serious. Look at the lines on this court.
Yeah, so what?
All right, well, let me ask you this. What is the longest possible shot on this court?
Well, if we were playing doubles, it would be from that far corner to that far corner.
That is a diagonal. Geometry.
That's right. You know, as a tennis player, you'd make a good mathematician.
Real cute.
Yeah, well.
All right, wise guys, is there any other way to do it?
Well, yeah, sure. Just the opposite, from that far corner to that far corner.
Which of the diagonals is longer?
They're the same.
You have just defined one of the properties of a rectangle.
I thought I'd just defined one of the properties of a tennis shot I have a lot of trouble hitting.
All right, now just suppose the diagonals weren't.
Weren't what?
Well, the same length.
You show me a tennis court that isn't the same length from corner to corner, and I'll show you a drunken groundskeeper.
Well, now, how do you know that?
I just know that if the corners are square, you know, it's got to be that way.
That's another part of the definition of a rectangle. Right-angle corners.
You and your dang geometry. Are we going to play tennis or not?
You know, there's another thing.
What?
If you were to serve a ball from one corner to the other corner, where would it cross the net?
I don't know where.
Right in the center of the court.
Okay, Todd, I will play your game. How do we know that?
Well, because half of a rectangle is a right triangle. The diagonal makes two right triangles.
If you say so. Todd.
And the net cuts right across the center of the court, and four right triangles are formed.
I believe you. I believe
now,
you.
two of the triangles have a base the entire width of the court, and the other two, the ones that are formed by the net, are similar triangles.
What do you mean similar?
Well, look, from the corner to the net, if the path of the ball forms a diagonal, that little triangle over there is the same as the big one, only smaller.
Yeah.
Well, it's the basic concept of triangulation.
Sounds like the basic concept of insanity.
No, really now, look at this court. Why, it's a regular geometry book. It's got everything. It's got acute angles, obtuse angles, squares, rectangles, right triangles, and the not-to-be-forgotten Pythagorean theorem. Why, even the ball's trajectory makes an arc. Why, everything's here but a circle.
Oh, what do you think this is? A little green apple?
A sphere.
A sphere. It's a sphere. Okay.
You know, when you look at that diagonal, it's easy to see why the formula for finding the area of a triangle is what it is.
It is easy?
Sure it is.
Okay, Todd. What is the formula?
Well, the area of a triangle is half the base times the height.
How's that again?
Half the base times the height. A triangle is half the size of a rectangle with the same height.
Okay, I'll buy that.
Sure.
Oh, I sure know one thing.
What's that?
Tennis sure was a lot more fun before we knew so much about geometry.
You know, then there's a direct proof, too.
Oh.
You knew that the corners of a rectangle were square by the diagonal. Then the indirect proof, you knew that if they weren't, you knew that if they weren't, it couldn't be a rectangle. Well, there's geometry everywhere. Look at your little radio here. Now, see, this is a regular rectangle. Can you see it here? Now, wait a minute. Oh, Lord. All right, if you don't want to talk about geometry, just tell me. I swear I can take a hint. Look, there's even a little triangle right in on your thing right there. See the little triangle pointing?
Steve Weiss again. Well, I guess geometry is where you find it. But Todd might have gone a bit overboard. However, he did make some good points. A tennis court does have a lot to do with geometry. If we follow what Todd said, we can learn a great deal about the laws governing the shapes of things. Here's what a tennis court looks like from above. Drawing the diagonal produces a right triangle. A right triangle has one angle of 90 degrees, which is called a right angle, and it has two acute angles, C and D. Acute means they're smaller than 90 degrees. The other diagonal is the same length as the first and forms a triangle just like the original one. Where the ball crosses the net, a smaller triangle is formed that looks like the larger one. Also, an obtuse angle is formed at C. An obtuse angle is one that is larger than 90 degrees but smaller than 180 degrees, so it's more open than a right angle. You will often see these same triangles drawn so that triangle B is flipped over. Your workbook uses this arrangement of triangles to illustrate how to measure the distance to certain places you can't physically get to, such as across a river or even across space. Check your workbook for formulas that tell you more about triangles. Well, I see Bill going in to visit Frank. Let's go and listen in.
Excuse me, Frank.
Oh, hiya, Bill.
How busy are you?
Well, I'm never too busy to talk to you.
Boy, you sure got a bunch of books there.
Yeah, geometry books. I'm trying to find one that's in between.
In between what?
In between basic and so technical that nobody can understand it.
Well, that is sort of why I'm here.
Oh, yeah? What's up?
I got a chance to upgrade my job at the plant, but I need to know more geometry.
Oh, yeah? Well,
You know, practical
I'll
geometry, not that stuff that's in books.
Oh. Well, yeah, a book is probably the worst place in the world to study geometry.
Teachers aren't supposed to talk like that.
I know it. We're not supposed to admit that the only reason we use books is to impress people with all those highfalutin sounding theorems and stuff.
Theorems like that Pythagorean stuff.
That's right. The sum of the square on the side of the hypotenuse is equal to the sum of the squares of the other two sides.
I always suspected you math people were snobs.
Yep,
Now
I'm afraid so.
I know it. Well, I still need your help. So if books aren't the best way to learn geometry, what is?
Go to the source. Ask the triangles and the circles and the rectangles.
And if I do, what will they tell me?
Well, now, you know that Pythagorean theorem?
Yeah.
Well, Pythagoras didn't really say that.
Is that right?
The right triangle did.
Oh. Yeah, sure.
I'm serious. No,
Frank.
I'm serious. All Pythagoras did was ask the questions and then write down the answers.
And that's what you want me to do.
That's
right?
exactly right.
Uh-huh.
That's exactly right, because sometimes having too much advanced knowledge messes up your detective skills. Wait, here. Take a look at this.
Okay. Well, I have seen this before in our machinist's handbook. You know, machinery has hex head bolts and stuff like that.
Uh-huh. Well, why don't we try asking a hexagon some questions?
Okay.
All right.
I'd like to hear this, what it says.
Okay, well, the first thing we have to do to make a hexagon is draw a circle, and we'll start with a circle that has a radius of 6 inches.
Okay, 6 inches.
Okay, so we'll draw us a circle, and then we'll divide it up into arcs, and we'll keep our same radius here on our compass,
Okay.
and what we should get is 6 parts. All right? And then what we do is connect the points.
Okay, I'm with you so far.
Okay? Now then, suppose we wanted to ask this hexagon, how can I draw you so that you will have 6 inches on each side? What would it answer?
You got me, Frank.
Well, now, take a good close look at the way I'm drawing this.
Oh, yeah, right. Right. So the distance you're marking off on the circle is the same as the radius.
That's right.
So if the circle had a radius of 6 inches, the hexagon inside it would have sides 6 inches long.
That's exactly right. So then, what would be the perimeter of this hexagon?
Perimeter, this is the distance around it, right?
That's right.
Okay, well, it has 6 sides, and each one is 6 inches long, 36 inches.
Good, you got that right off. All right, now what would be the area of this hexagon?
That is a good question. I guess there is a formula for it, isn't there?
Yeah, I suppose so. I don't know what it is, though.
Well, I know the formula for the area of a circle. It's pi times the radius squared. I memorized that.
Well, that is a good one to memorize.
And it looks like the hexagon would be smaller in area than the circle it's inside.
So, how would we go about finding the area of this hexagon?
I don't have any idea.
Well, how about this? If I don't know the formula for finding the area of a hexagon, what if I break it up into other shapes that I do know the formula for finding the area of?
You mean just cut it up?
Sure. Here, you come and do it.
Okay.
You come and do it. All you have to do is to divide the hexagon up into shapes that you recognize.
I'll give it a try. Let me see. I'll just start off. I'll just draw a line straight across it, right through the center. Now that, I don't remember the name of that, but I do recognize that shape.
That's a trapezoid.
Trapezoid. Is there a formula for the area of a trapezoid?
Yes, I think so.
Okay. All I have to do is find that, multiply it by 2. I have the total area of the hexagon.
You're right.
Okay. What is it?
What's what?
The formula for the area of a trapezoid.
I don't know. Well, now you have to divide that shape up into other shapes that you can find the area of.
Okay. Let me see. Draw another little line here, right to the center. Now, what is the name of that shape?
That's a rhombus.
that
But I don't know the formula for that either.
Okay, well, that is a triangle. I know that. Wait a minute. Draw that line straight through. Draw a line. Ah, there's 6 of them, 6 triangles, just like that in the hexagon.
Well, now, do you see what that hexagon's telling you? It says 6 equiangular equilateral triangles.
Hexagons sure use big words, Frank. Do they have to do that?
Now, do you know the formula for finding the area of a triangle?
Oh, yeah. Todd was telling me that just the other day. He told me not to forget it.
And you forgot it.
Now, wait a minute. It's 1/2 the base times the height. Yeah, now, I can see that.
See what?
Well, triangles are half a rectangle. So to figure the area, you use the height, but the base is only half as big.
Show me.
Okay, if you had a triangle like that, and you divided it in 2 like that, now if you took this side, cut this side off, and moved it around, turned it upside down, it would fit on the other side just like that. So what you end up with is a rectangle, but these 2 sides are only half as long as the base of the original triangle.
So, you got the answers from the triangle, the rectangle, and the circle.
Right. But I still don't know the area of the hexagon.
Well, do you want me to tell you the formula?
Nah.
Why not?
Well, you haven't given me a single formula so far. I'll just wait and get it from the real authority. The hexagon itself.
Good. But keep asking, though. You never learn anything if you don't ask questions.
Yeah, I'll give you that. Well, I have found out that the answers are in the shapes themselves. The rectangle, the triangle, the circle.
Right. But don't underestimate Pythagoras.
Oh, I won't. I'm getting more respect for this guy all the time. Do you know him?
Sure. He runs a restaurant down on Main Street.
Oh, I thought maybe he taught here.
Bill is learning how to ask questions about various geometric figures, isn't he? Some of the answers appear to be a bit complicated, but he is on to the idea. If he can find the area of one of the triangles within the hexagon, he can then figure out the area of the hexagon, because a hexagon is made up of 6 triangles. Let's review some of what Bill has discovered about rectangles and triangles. Here's a rectangle and the formula for finding its area. That formula is the base times the height, and it means you multiply the measurement of the base, one of the shorter sides, times the measurement of the height, one of the 2 longer sides. The product of that multiplication is the area inside the rectangle. In order to find the area of the triangle inside the hexagon, Bill must use the formula 1/2 the base times the height. Look closely at this illustration and you'll see that the area of a right triangle is half the area of the rectangle that has the same base. In computing the area, Bill first has to find the height or altitude of one of the triangles inside the hexagon. And the altitude of any triangle is always at a right angle to the base. So this dotted line shows you the altitude of this triangle. To actually measure the altitude of this triangle, Bill can use the Pythagorean theorem. Watch now as we overlay the drawing of the Pythagorean theorem on top of the triangle within the hexagon. You can see from this that Bill can use the theorem to start his calculations for the area of the triangle and then figure out the area of all 6 triangles that make up the hexagon. And now you know why Bill said he was learning to respect Pythagoras. Figuring out the questions and then using the answers given by the figures isn't always that simple.
As soon as I recognized that a hexagon is made up of 6 equal triangles, I knew I was on my way.
But how would that help?
Well, I know the area. I know how to find the area of a triangle. The formula is area equals 1/2 base times the height. Now let's pick out one of these triangles, this one. The base across here is 6 inches. All of these sides are 6 inches, as a matter of fact, because the radius of this circle is 6 inches. Now, the problem is finding the height. This would be it right here, but I don't know how to figure it out.
Isn't it the same as the other lines of the triangle?
No, unfortunately it isn't, because, see, what we've done when we divided the triangle like that is we made a right triangle, and this leg of it becomes the hypotenuse of that right triangle, and that is the longest leg in the triangle.
So that's where the Pythagorean theorem comes in.
Right.
Great.
I brought in this chart that illustrates it very colorfully. According to the theorem, in any right triangle, the area of the square on the hypotenuse is equal to the sum of the squares on the other two sides. The formula is usually written c squared equals a squared plus b squared. Let me put that down. Now all we have to do is start substituting these values in the formula. We're on our way. Now we know that the hypotenuse here is 6 inches. 6 squared is 36, right? Equals, now we know that this entire side of this equilateral triangle is 6 inches, and of the right triangle that we're dealing with is 3 inches, half that, or 3 inches. So 3 squared is 9 plus b squared. B is what we're trying to find out. Now what do we do?
Well, I see. This is what we were doing a couple of days ago. You just subtract 9 from both sides and you'll get what b squared is.
Right. Subtract 9 from both sides of the equation, like this, and we get 27 equals b squared. Now, if we could just find the square root of 27. Martha,
I've got
you
my
have your calculator handy? We'll be taking the square root of each side of the equation, and b, remember, is the height of this triangle. You have it, Martha?
Okay, b is 5.196, so why don't we just make it 5.2?
Good idea. b equals 5.2 equals b. Now, we can substitute these values in the equation for the area of the triangle. The triangle is 6 inches across the base, so it would be 1/2 the base, 1/2 6, or 3 times the height, which is 5.2.
So then the area of that one triangle is really half the base, or 3 times 5.2.
Right.
Okay.
Right. Martha, what is 3 times 5.2? These calculators are wonderful.
15.6 square inches.
Right. The area of this triangle is 15.6 square inches. And that means that we're almost home free. Just one more step. Since the whole hexagon consists of 6 of these triangles, the total area of it would be 6 times 15.6 square inches. Martha,
And that
if you'll do the honors.
93.6.
The area of the whole hexagon is 93.6 square inches, and I can't believe I calculated the whole thing.
All right.
Well, I'm impressed, Bill. I'm very impressed. You've really learned a lot about algebra and geometry. You all have.
There's something I've been wondering about.
What's that?
Why do we use squares to express the area of a circle?
Now, what are you talking about?
Well, the area is always expressed in a certain number of squares of a certain size that'll cover the surface, right?
Right.
Well, squares won't fit in a circle. There's always those little oblong-shaped things left over on the edge. So why do we use squares?
Oh, leave it to Todd to mess things up. Can't you just learn the formula?
Yeah, he's right, though. The squares never fit exactly into the circle.
Oh, now
Right.
wait. Now, what if I made a circle out of pie dough and cut them into squares, and then took all the little leftover crumbs and made them into squares the same thickness as the others? Wouldn't I have the area of a circle in squares?
Well, you would probably have a very good approximation.
Approximation, but math's supposed to be precise.
Yeah, it is. It's supposed to be. But circle answers are always approximations.
How come?
Well, okay, I'll try to explain. But first, what is the formula for finding the area of a circle, Martha?
It's pi equals the radius squared.
That's right. Now, all of you remember that, all right? Remember it. Okay, now first, circle answers are always approximate because pi itself is approximate, right? We always round pi off before we use it, right? Okay, now Bill, what kind of measure did you use to express the area of that hexagon?
Squares.
And it didn't bother you to express the answer in squares?
No, because squares and parts of squares can be made to fit into a triangle, and I started off using a triangle.
That's right. Now, you said you had to find the altitude or the height of that triangle before you could find the area.
Yeah, right.
All right. Now, what if that had been an octagon instead of a hexagon? How would that affect the height?
Well, the height is closer to the length of the radius. Hey, I just noticed something else, too. The octagon is closer to the size of the circle. There's not as much waste around the edges.
That's right. That's very perceptive, Bill. Now, what would you speculate then about this 12-sided figure?
It's even closer to the size of a circle.
That's exactly right. And look what happens to the triangles that make up that figure. You see, their height is even closer to the radius.
Well, that shape's even closer to looking like a circle.
That's right. Now, what if you had a polygon and that polygon had an infinite number of sides inside this circle?
Well, then you couldn't tell the polygon from the circle.
And the triangles would be so small that you couldn't tell the height from the radius. But you could still consider it as having triangles in there. Huh? All right. So if Bill can use a certain number of squares to express the area of a six-sided figure, the hexagon, why couldn't you use squares to express the area of a figure that had an infinite number of sides?
Well, now that sounds logical, but how do I know what that number of squares is?
Let's try one. Here is a circle that has a radius of 7 inches. All right? The area equals pi times the radius squared. We know that pi is equal to approximately 22/7, and 7 squared is 49. So the area is
154 square inches.
154 square inches. Now, does everybody follow that?
Yeah.
All right, all right. Now, what if I wanted to build a rectangle that had one side that was 7 inches and still had the same area as this circle?
Well, you divide the area, 154, by the radius, or 7, and that would be 22. So the area of a rectangle with 154 square inches would be 22 by 7.
Like this.
Yes, that's it. Now I know that has 154 square inches, but how can I really be sure that's the same as the circle?
Well, that's a good question. Would you believe circumstantial evidence?
Yeah. Sure, I'll accept that. 22 and 7, 22/7, that's pi. There does seem to be something like pi in those proportions there.
That's absolutely right, Bill. That's a good idea, too. Don't forget that. We'll be coming back to it.
You mean there is actually some real connection?
Yes, you bet. But now, first, I want to construct a right triangle that has the same area as this rectangle and one side of 7 inches.
Well, that's easy. If a right triangle is half a rectangle, then to get the same area as a rectangle, you'd have to double something.
All right, good so far.
So if you keep the base at the same, at 7 inches, then you're going to have to double that side. So we're going to change 22 to 44, and then multiply that by half of 7, which is 3.5.
Now, wait a minute. The area equals 1/2 the base times the height, so you multiply by
Half of 7, which is
3.5.
right,
Right.
and then times 44.
All right. And the answer is?
154 square inches.
You're fast, Martha. All right. Now, that is the area of this triangle, huh? Huh? All right. Now, I want to make one more tie-in here. It's your turn, Martha.
Okay.
Now, we've been talking about this circle here that has a radius of 7 inches, all right? Now, that would mean that its diameter is 14 inches, right?
Right.
All right, we know the formula for finding the circumference of a circle is the diameter times pi. So what is the circumference of a circle with a 14-inch diameter?
Okay, I multiply the approximation of pi, which is 3.1416, times 14, the diameter, and it's 44 inches.
Hey, that's the same length as the side of that triangle.
Well, so it is. Now, do you think that's a coincidence? Huh? Let's look at some of these things, all right? Here we have a triangle, or a rectangle, with sides of 7 inches and 22 inches and an area of 154 square inches. Here we have a triangle with sides of 7 and 44 and an area of 154 square inches. And here we have a circle with a radius of 7 inches and an area of 154 square inches.
And don't forget about that triangle that has the same side as the circumference of that circle.
Right.
There must
right.
be some kind of connection here. We keep hearing the same numbers over and over again.
Frank, let me see if I got this straight. There's certain numbers in a circle, right? It's dimensions, measurements.
All right.
You can take those same numbers and use them to find the area of other shapes like triangles or rectangles.
Yep.
And those shapes can be divided up into squares.
That's right.
So even though we can't make all the little squares fit exactly into the circle, we can use those same squares to find the area of the circle.
Now, do you agree with that, Todd?
Well, you know me. I'll have to think about it.
Well, all right. But if you don't believe us now, go unravel an orange.
What?
Think about it.